introduction to virtualization, because we need to also look into virtualization and how code works in virtualized environments. But it's simply an introduction part. As we go into drivers and kernel programming, we'll explore more about this area, because this is one domain, one specific issue that's being targeted by almost all the hardware vendors, where most of the processors today which are virtualization enabled. And then hypervisors are there in real-time operating systems also. So we'll just get started with that. I'll just give you a brief introduction to it. And then we'll go into tools, GNU tools, and how to use compilers, linkers on Linux and so on. So this is an extension to what we have seen yesterday. Yesterday we have looked into types of operating systems, that is, where they are used, embedded real-time and GPOS. And then we have understood what Linux is. Linux is simply open source kernel which can be made into an operating system, and distributors are the firms which are involved in this business of making an OS out of Linux and then distributing and supporting it. And then we have understood the monolithic and microkernel architectures and Ring 1, Ring 2 for the middleware services called drivers and file systems. So we'll look into an extension for that. Before we go into this one, what is the primary functionality of kernel now? Many functionalities are there in kernel. What is the primary functionality? If you have to identify one primary job of kernel, what would be that? Scheduling, managing resources, services. So many are there, but the most vital and the most important is obviously managing resources. Managing resources so that the resources are available and shared by the applications. Because we understood this yesterday, users are interested only in applications. Users are not directly interested in the functionality of kernel. It is the kernel's job to maintain resources and to share the resources between the applications which need them. So resource management is a typical job of one of the primary functionalities of kernel. Around resource management, scheduling, drivers, all these fall into that primary job. Scheduling is simply one resource called CPU resource is being managed by scheduler. Similarly, I/O resources are managed by device drivers, isn't it? So resource management is the key and primary role of an operating system's kernel. Now in the case of you can summarize it that way. We have hardware with all the architecture and all that. On top of it, an operating system's kernel. On top of it, we may have n number of applications, different types and different number of applications. Now these applications, whenever they need resources, they cannot directly access resources because they are always in ring 3. Irrespective of type of kernel, applications are always in ring 3. That's what we understood yesterday. So these applications will fall back on the kernel, which is in ring 0 always, for the resources. And these resources are managed by the kernel. Two applications, if they want the same hardware, the kernel should make sure that both of them have the access to hardware without a conflict. The kernel's job is doing that resource management. Now, virtualization, simply put it like this. Let's make an assumption that we have multiple operating systems to be used. We want to use multiple operating systems so that we can actually run specific set of applications on each of them. Let's take a case of Windows and Linux. You have a requirement of running few Windows applications and few Linux applications on the same hardware. So virtualization is simply using the software, installing multiple operating systems, and sharing the resources between multiple operating systems. Each operating system is called a guest or a specific domain, domain 0, domain 1, and so on. So virtualization is simply we take out the OS from this particular ring 0 and we use the software, basically a piece of code which is called hypervisor. This piece of code now becomes the manager. It will manage all the resources, in turn share them between multiple operating systems. So simply put, virtualization is a technique of enabling multiple operating systems to reside on the same hardware platform. And again, hypervisor is nothing but kernel. Kernel specifically implemented to manage resources for other kernels. Normal kernels are implemented to manage resources for applications. Hypervisors are kernels implemented to manage resources for various kernels or various domains called virtual machine domains. Okay? So, don't take that. We'll start with this diagram. Take this diagram. Just write down virtualization introduction. This is simply to understand why virtualization is needed. So first we start with an assumption that we have a requirement of using multiple OSs. When you have a requirement of using multiple OSs, that could be because of security, that could be because of a specific type of applications that you are using, or that could be because of multi-core hardware that you have and you intend to run this multi-core hardware with multiple operating systems. Different reasons to go for multiple OSs. The concept of sharing a single platform, or what we mean by platform is this hardware with a specific architecture. The reason why we should know about this, because system programming also means you could be working on virtual machine level, writing drivers for a virtual machine, or doing some service development for a virtual machine. That also is one of the areas today. Lots of companies are involved in building their own VMs. Software point of view here. If you look at this from hardware point of view, hardware designer's point of view, or embedded developer's point of view, embedded hardware designer point of view, they go for virtualization based on what kind of hardware they have. It could be multi-core or type homogeneous or heterogeneous and so on. Right now, let's not talk about it. In our classes, what we'll do is we'll think only on the software side. Later, in the embedded, I'll give you exposure to hardware side decisions, like why do you go for virtualization and decisions taken to go for virtualization because hardware needs it. So those we'll see later. Heterogeneous multi-core, homogeneous multi-core, DSPs and processors, specific processors. Those things, we'll not talk about them here. This is software side. Assumption is you have a requirement of running multiple OSs. Now this is very simple. The diagram is simple, but what you need to understand from this is this. Hypervisor, though the name is different, it is same as a kernel. So what components go into a kernel? Almost the similar components go into hypervisor. Kernel development and hypervisor development are similar. So from system programmer's point of view, from kernel developer's point of view, it is simply a piece of code similar to kernel with some drivers, with some file systems, with some specific instructions to host multiple OSs. Instead of hosting application, you're hosting OSs. They are called guest operating systems. Okay, now how this is done? This is done by writing a set of drivers called virtual drivers. Yesterday we understood what drivers are. Drivers are basically middleware services which are used by the applications to access the hardware. In traditional operating system setup, drivers are in ring 0 in the case of monolithic. In the case of micro, they are in ring 1 or ring 2, isn't it? In case of hypervisor, they will be in hypervisor, and these drivers which are in the hypervisor are called virtual drivers because they emulate the hardware. There is a slight difference between driver development here and driver development here. Almost all the drivers which reside here are emulation drivers. What these hypervisors do is this. To enable virtualization, they allow the users to create virtual hardware. Like those of you who have used VMware. If you have installed VMware, the next thing that you do is configure a virtual PC. You mention how many processors should be allocated for it, how much of RAM should be allocated for it. So within the same PC, in the same platform, you're configuring a virtual PC. And the key point is, whatever physical hardware you have, the same physical hardware need not be emulated. Say for instance, a VGA card of NVIDIA. Here in the virtual machine, I can emulate it as ATI. It's possible. So Virtual machines use virtual drivers, and hypervisors use virtual drivers to emulate the physical hardware and to allow creation of a virtual machine. Okay? So driver developers here are writing basically drivers of type virtual, not physical device drivers. So I'll talk about in device driver classes how to write virtual drivers also. That's the reason why I'm introducing this concept here. So these are virtual machines. If you've taken the earlier diagram, you can just take a small arrow and add up these blocks. So each guest OS is assuming that this is the real hardware. It does not know about the existence of hypervisor. It assumes that this is the only software on it. This partition is different, this partition is different, memory is partitioned. One domain cannot access the area of other domain. That also is taken care of. Those of you who are curious to explore more, you can try one thing. You can install VMware kind of virtualization software and some other virtualization software on a PC with Windows or Linux installed in it. Two virtualization hypervisors. And configure virtual machines in both of them. And install a guest operating system of your choice in both. Boot up the first guest and see the device list. All the operating systems allow you to see the device list. You will see the devices which appear there will have a different vendor identity than the physical devices which are connected. That's where you get a complete clear picture about what virtualizing means. Emulation. So each domain, if you try it on the first virtual machine, you'll see some other devices. If you try it on second virtual machine, you'll see some other devices. VMware has got some virtual drivers. Irrespective of whichever VGA card you have, they emulate that with their virtual driver for VGA card. So like that you can verify. But that's not needed now. As we go on, I'll explore more about this. I'll give you more details about how do you write drivers. The reason why I'm presenting this is we should treat hypervisor simply as a kernel. And we should be able to write code if needed in hypervisors also. For that reason I'm introducing this. So now there are two types of hypervisors. Just to add more information. There are two types of hypervisors. Type 1 and Type 2 they are referred to as. Type 1 is they reside directly on hardware. There is no host operating system. The hardware, on top of the hardware we have the hypervisor, on top of that guest operating system. This kind of virtualizers are called, or this kind of hypervisors are called bare metal virtualization. Embedded domain, most of the implementations use this. Server-side market, PC market, they use this. In this what happens, you have an operating system like Windows or Linux installed. That's called the host OS. On top of that you install hypervisors. This is a usual practice on the server domain and desktop domain, so that you can have multiple OSs running. This is done to load share the resources. This is done to develop the applications for cross-platform and test them and debug them, all that purposes. So this is called Type 2 hypervisors. Type 2 hypervisors, they reside on top of a host OS. Type 1, they are bare metal. Two types of hypervisors exist, but this is a usual practice on embedded and real time. And this is a practice on most of the desktops and PCs. Even some real-time PCs, they use that. Okay. Just take down that practice. Examples that you can relate to: VMware Workstation, VMware Server, Virtual PC from Microsoft, Zen, the Zen initial versions, and then KVM, they're of that type. It's possible. Talking about this one? Yeah, it's possible. Hypervisors today allow the applications to be implemented which run directly on the hypervisor. That's also possible. What is this? Hypervisor itself is OS. That's what I'm telling you. Though we are using a different term to relate to it, basically it's an OS. Difference is it can host other OSs. Because it can host other OSs, we are using a different term to relate to it. But from system developer point of view, this is also an OS. So when you say it's an OS, it should be able to support applications as well. In embedded, what we do, we run some applications specifically in hypervisor for performance, real time. And non-real time part of it, we take into an OS and implement it there. And this is usually portable. This is specific. You can have multiple OSs also. You can have multiple OSs also. There's no need for you to have only one OS. You can configure as many virtual PCs as you want. But normally on desktops and servers, what we do, we use each hypervisor as one virtual machine. You can create any number of virtual machines inside it, but only one you can boot at a point in time. Say for instance a Windows PC. I want Linux and I want Solaris, both of them parallelly. I'll install VMware and then configure one virtual PC for Linux, one virtual PC for Solaris, and move them. It's also possible. Since these are desktop level, in desktops we use 2 OSs at a time. That's the reason this model is being shown this way. So these two together could be one instance hosting multiple OSs. Here the view is, what you need to understand here is, this is a virtual PC, this is a virtual PC, 2 OSs. This could be VMware, this could be VMware. But in type 2, difference is hypervisor is an application. In type 1, hypervisor is a supervisor. That's the difference. Which one will give more performance, type 1 or type 2? Type 1, quite obviously, because type 1 is directly interacting with hardware. So now you know rings. You know rings. Where will this go? Where will the type 1 hypervisor go? Which ring? Ring 0. And guest operating systems can go into ring 3 or ring 2.1 because they are simple applications. Okay? Here, ring 0 is where? OS, host OS. And hypervisors will be in ring 3. So performance will come down here. But the benefits, you have good amount of hardware power on PCs. So it works fine for the PCs and server side. On embedded, this architecture will not work. So terminology is simple. What we refer to as a kernel, normally we are referring to that as a hypervisor and virtualization. That if you carry, then hypervisor is simply one type of kernel. So this is about the basic types. Here with these types, type 1 and type 2. Type 1 usually implemented on real-time OSs and embedded. Real-time and embedded platforms, type 1. Type 2, server and server and desktops. Just to know, for information, can you think of any benefits with this? 1, 2, 3, 4 like this, as many as you can. Can you think of any benefits with this kind of software architecture? What was the benefit of having the privilege levels yesterday's session? Security from what to what? You have the ability to split up the memory and then put applications in isolated zones so that one application crashes or one application's problem does not affect the rest of the applications of the kernel, isn't it? Now with that, similarly with that, when compared to that, can you think of any benefit of security here with this virtualization? You may have some applications which are critical, which should go on in a completely isolated segment, right? You can have virtualization enabled, put your critical applications into one zone, which will not be available for access from the other zones, and divide non-critical here. One could be RTOS, one could be GPOS, isn't it? In the traditional setup, either you can have an RTOS or you can have a GPOS. With this now, you can have RTOS running critical applications in secure zone, a GPOS running non-critical software in normal zone. Okay with this? Like this, you can have multiple types of OSs, not just Windows Linux. You can have an RTOS with a GPOS service. There are many embedded projects, or there are many real-time projects, where the real-time code is 60%, non-real-time code is 40%. If you choose an RTOS for that kind of platform, only 60% of your code is using the RTOS services, and 40% of code needs the services of a GPOS. So those GPOS services will not be available usually on a RTOS. So here what you can do, you can have the RTOS along with the GPOS. That's the benefit, type 1 benefit. Take down the benefits of virtualization. We'll just figure out 3 to 4 just to understand. So benefits in the embedded domain, benefits in the real-time domain is a GPOS can be used alongside an RTOS. Benefit 1. GPOSs can be used alongside an RTOS or embedded OS. The GPOSs can be used alongside RTOS and embedded OS. Mobile phones already are using this. Android part of it runs on real-time kernel, and the rest of the non-real-time part runs on virtual Linux. Like this, most of mobile phones are using it already. Symbian with Linux, Android, and Linux Android in one area with some other Windows kind of operating systems in the other virtualized environments and so on. That's possible. Second benefit. Security for critical software. This I'll show you practically. This I'll go into more details and explore, especially in real-time systems. This is needed. Security at highest level, and that can be achieved through hypervising and virtualization. Third one, on a desktop, why is it needed? On a desktop, like a PC, can you see any benefit of this? Let's make an assumption I use Linux, and for some reason I need to make use of Outlook kind of software. Now Outlook doesn't run on Linux. You can install Windows on top of it and then use Outlook along with Linux applications side by side, isn't it? So all this is possible on desktop. Also, developers, application developers writing applications for Windows will be using Windows PCs. If they have to write some applications and test for Linux, they can install the virtualization with Linux and build applications and test there. Sometimes you may write applications which are portable, targeting multiple OSs. Now when you test them, you got to test them in setup 1, take it again, put it on setup 2, test it there. If your virtualization enabled, testing also is possible easily on the same box. Okay, so testing, debugging, from developers' point of view. For application developers, the benefits for application developers to assist. For application developers to assist testing and debugging. Testing, so developing, testing and debugging, all three. Developing, testing and debugging. Developing, testing and debugging. Portable applications. Portable applications. Where both of them parallelly, yes. If one is booted, other one is shut down, the dual boot that we use, they're not. If they are side by side hosting different applications working on same machine, it is possible only through virtualization, either type 1 or type 2. Clear so far? Okay, now we'll look into one more issue. I'll take you into details of all these in the coming driver classes, but one more issue is there that we need to understand. Now, what you need to understand is, when this particular operating system makes a call, it is taking this as hardware, isn't it? So a driver here will try to manipulate the hardware state. Let's make an assumption there is one driver here trying to talk to VGA card, the virtual VGA card. Hypervisor should take that instruction and then pass on the instruction to this one. Similarly, if two operating systems are trying to access the same device, hypervisor must take those calls and then create a kind of mutual exclusion, so that once one instruction of one of the domain is executed, other one is pushed into wait, isn't it? So this must do all interception. What interception? interception of instructions which are being carried out by services which are in these domains. So one of the most important jobs of hypervisor, intercepting a call to hardware and translating that into which one? This particular hardware. Because there are hypervisors which allows emulation of a different architecture also. In type 1 there are two types of hypervisors in type 1. One is called native virtualization mode, where if this is Intel architecture, this will emulate Intel architecture. The type 2 is other mode called the normal virtualization mode, where if this is Intel, here it will emulate ARM. Here if it is Intel, it can emulate PowerPC. So emulation mode is 1, native virtualization mode is 2. In this there can be both of them. Emulated mode, PowerPC instruction should be converted to x86. So translation will be needed in the emulation mode. Native virtualization mode, directly take it, verify who is calling, and then translate and give it to this. This is simply, the native virtualization mode simply is faster when compared to emulation mode. Just make that additional point. There's one more point that we need to understand after this. We are interested, most of the time we'll be interested in this, because this is the one that's widely used in embedded and system programming areas. Type 1 hypervisors, type 1 hypervisors type 1 hypervisors can be implemented using emulation approach, architecture emulation approach, that's approach 1, and native virtualization approach. If you want, you can describe each of them in short. Emulation approach involves hypervisor emulating different hardware architectures, for virtual machines to be configured. Example, allowing a virtual machine with PowerPC architecture. Example for this. Allowing a virtual machine with PPC architecture. Allowing a virtual machine with PPC architecture to be configured. Allowing a virtual machine with PPC architecture to be configured while on Intel x86 machine. While on Intel x86 hardware. So here, this is actually the slowest implementation. This is used always for testing in embedded. Okay. So we have an Intel platform here or a PPC platform here. Here we emulate ARM, and then we have an ARM OS installed on top. In this, what happens is each call should be translated from the target architecture to host architecture. This is the first time. Second approach, native virtualization. For this approach, native virtualization is the emulation of host architecture. Native virtualization involves emulation of host architecture to allow virtual machines, allow host architecture while configuring virtual machines. VMware, most of these always are native. most of these. These are either native or emulated. Now, where will this be in ring 0, isn't it? Obviously, this should be in the supervisor mode. Where will these be? Ring 1, 2, or maybe in ring 3, depends on the design. Now, emulation means, or emulation or whatever, native. A call from here to here is one mode shift, and interrupt could be involved in it. And then from here to here, one more access, isn't it? So each call has to be intercepted and translated if required, or mapped. In emulation, we translate. In native, we map. Map means what? The actual VGA card is Intel VGA card. While configuring the virtual machine, we have configured it as some other vendor, X vendor VGA card. This driver here is X vendor's driver. X vendor driver will make an operation on the VGA card of X. There is no VGA card of X. Actually, we have Intel. So that should be mapped to Intel's call. That is what happens in native virtualization, and mapped from these instructions to host instructions. In emulation, what's happening is translation. Translation from this type to target architecture type to host architecture. So slowest will be always emulated ones. Native ones are faster. Mentioned that last point. Wherever you feel important, take down and just continue. Native virtualization provides good performance. Native virtualization provides good performance over architecture emulation virtualization. Another benefit with the native virtualization is this, especially on the embedded domain. If one of the virtual machine is using VGA, other virtual machine is not using it. Let's make an assumption, VGA is not configured for that. Then we can allow this operating system of virtual machine to directly talk to VGA instead of vmapping. So we can allow, wherever possible, this hypervisor can allow direct operations when there is no conflict. When there is conflict, it will simply do nothing. The performance always of native virtualization is faster and higher when compared to emulation. Okay? Now recently what happened, almost in all the hardware architectures in CISC and RISC, it was like this in the earlier kernels. Kernel here, applications here. Yesterday we have seen this. Later, they had these two models till recent past. One model was this, the other model was this. Those virtualizers. One model, hypervisor will be in always ring 0. 1, 2 are left empty, and the guest OSs can be in 1, 2, and the applications are in 3. This is called 0, 1, 3 mode. 0 is hypervisor, 1, 2 for guest operating systems or virtual domains, and 3 for applications. The other implementation is 033 mode. 033 is where hypervisor is in 0, and guest operating systems are in 3, and then applications also are in 3. This is what happens in VMware on PCs. This is happening on the embedded. And the problem here is, since the guest operating system, in both of them there is the guest OS. In one of them guest OS is in 3. In the other the guest OS is in 1 or 2. So a call from the guest OS to hypervisor requires a shift. So performance penalty will be there. Here it is more. Here it could be reduced. Isn't it? So recently hardware vendors, the processor vendors, both RISC and CISC processor vendors, they came up with a technology to support virtualization and the host operating system or guest operating systems to sit in the same privilege layer. Okay, that's called virtualization enabled processors. Intel Core i3, Core i5, Core i7 are the examples of it in the case of PCs and server side. In the embedded we have ARM processors of that type. In PowerPCs we have PowerPC of that type. So this is called hardware enabled virtualization. Hardware enabled virtualization simply means processor designed in such a way that it allows the host operating system and that particular hypervisor to reside in same rings. so that communication between them can be reduced without a mode shift. So that's what hardware assisted is. Just mentioned the last point, this one. So two ways you can have virtualization configured. You can configure virtualization on the hardware which is not designed to support virtualization. You can also have virtualization on the hardware which is designed to support it. Code studios on the PCs, they were not designed for this. They were of this type. Intel i3, i7, i5 processors that we see today, they are of this type. Intel calls it as Intel VT technology. VT is virtualization enabled technology. So there what they do, they have a ring called ring -1, which is virtual ring. It's not a physical ring. Virtual -1 is some part of 0, where the hypervisor resides. And 0 is where the guest OS resides. Communication between them does not require a mode shift. Okay, so it is faster now. Put this idea, hardware enabled virtualization or hardware assisted virtualization, whatever. It's fine, we take that. Hardware assisted virtualization. And take down just one point. Almost all the processor architectures, almost all the hardware architectures, risk and both. Almost all the hardware architectures support virtualization technology from processor modes, from processor protected modes. Virtualization technology from processor modes by allowing hypervisors and guest OSs to reside in ring 0, or in the bracket supervisor mode. So only can take down that data. The first approach which was there, which is still used on those CPUs there, that is called ring deprivileging. Ring deprivileging means put the guest operating system in deprivileged area. Put the guest operating system in normal areas. Privilege zone is which one? Ring 0. So put the desktop in ring 1, ring 2, that's called deprivilege. Deprivilege the guest operating system from directly accessing hardware, so that this particular virtualizer can take the calls, intercept and map or translate. Right? Here what happens is, this can carry out few operations on its own. If required. It will fall back on this particular hypervisor for few operations. At configuration time, we can mention what operations the guest can do directly, what operations it should do through ring 1 or ring -1. The reason why we need to know all this, because we could be writing code here also. That is the only possible reason why I am talking about all this. Otherwise, from user point of view, all this is administration configuration. Yes, that's where a lot of things are happening. What's happening these days? The guest OS vendor is providing a hypervisor for this kind of blocks. And there should be a standard evolved. Otherwise, these two, if they don't coordinate and work, then things will not work. That's the reason most of the outsourced vendors like QNX or Integrity, if you look at most of these websites, they ship their outsource along with the hypervisor. For compatibility reasons. And if you are using two different vendors' products, they should be standard, so that both the products are implementing the standard for interoperability. We'll go into details of this in programming. Right now it's just an overview. The conclusion is this. Kernel programming is about writing kernel services. Microkernel we have seen, monolithic we have seen, virtualized kernels we have seen. For us, hypervisor is simply another kernel. Okay, now, so we have three types of drivers now. Microkernel drivers will be in, or drivers for ring 1, 2. These drivers should offer an IPC interface to applications. Right? Then drivers for ring 0, monolithic kernel. These drivers should offer a system call interface to the applications. And drivers or hardware access code in ring -1 or in this type in hypervisor zone. Most of those drivers should do mapping or translation. So drivers should do that. Drivers should emulate a device. Any operation on that device, take the operation code, opcode and map it to the physical device in native virtualization mode or translate it to host architecture in case of emulation mode. So different ways are there, different approaches are there, different issues are there while writing device drivers. Okay. This course, what I'm doing is I'm touching all these domains. All the earlier courses 1 year back and all, we used to speak only about Linux device drivers for monolithic kernel. Now in this batch and the previous batch before this, in the morning sessions, I'm talking about all these three types of drivers. That's the reason we should know substantially about applications first. Because any case where the applications are, virtualized case, non-virtualized case, applications are in ring key. So when you use APIs, we must know how the communication across these rings is happening. Then it's easy for us to implement case-based code. Okay, or the virtualized, or the ring code, ring 0, ring -1 code. So this is the simple introduction. Any questions? If you want, you can take 2 minutes time. Take a recap of what all I spoke from yesterday till now. The only thing that I want you to know is you must be clear about what is kernel. You must be clear about what components reside in the kernel, types of kernel. Yesterday, monolithic, micro. Today, virtualized kernels. So 3 types of kernels. On the second topic of this essentials. The first topic is introduction to what an OS is. Till now what all we have seen is simply introduction to initial understanding of what OS is. And we have spent some time understanding kernel and various forms and shapes it could be in. Right? Now we look into basic set of tools. This